Hey guys, so this is work and power. This is unit 5, video 1, okay, on the energy unit. All right, this is the first video, okay? So today our goal is for that you should be able to define work. It's different than like the common way that we use the word work in like regular language. So we want to be able to define work in physics. We want to be able to relate work and energy on an object. And we want to be able to solve for power. Okay, so let's just get started here. So when any two bodies, so two objects in the universe interact, they can exchange energy, momentum, or both. Okay, in this unit we're just talking about energy. All right, we typically decide to use energy when an object is moving or has the potential to move. Okay. If energy is put into a system from the outside or energy is taken away from a system, it is often in the form of work, which is a transfer of energy. So if we're going to define work here, we would say that work is basically how energy is transferred from one system or object to another. Okay. Okay, the equation for work, and we use big W, all right? The equation for work is force times displacement. All right, pretty simple equation, force times displacement, which makes the units pretty easy. So the units of force are newtons. The units of displacement are meters, okay? And so we can say Newton meters, or we actually call this a joule. Okay, so a Newton meter is a joule. Okay, so we're in joules of energy. And we use big J to represent joules. It's named after a person. Okay, so since work is a transfer of energy, work and energy have the same unit. Okay, so both work and energy will be measured in joules, okay, or Newton meters, but joules is the more commonly used one. All right, so let's just do a quick example here. A 5-kilogram box, so mass is 5 kilograms, starts from rest, is pushed with a force of 200 newtons over a distance of 15 meters. How much work was done? Well, the mass doesn't matter because it's not in our equation, so we're not going to use that. So if we want to know the amount of work, we have the force times the displacement, okay? And that will give us, I think it's 3,000 actually, 3,000 joules. How much energy does the box have? Well, it started from rest, so it had no energy. It was just sitting there, right? And then it got pushed with 200 newtons over this distance, and so energy was given to the box in the form of this work that was done. So if there was 3,000 joules of work done, then now the box has 3,000 joules of energy. Okay? So if you do work on an object, you're transferring your energy to that object. So whoever pushed this box transferred their 3,000 joules to the box. And now the box has 3,000 joules of energy. Okay? This is kind of a horizontal example. Here's a vertical example. Okay? A boy lifts a 30 grams, so mass is 30 grams, which we don't like, right? So let's just change that to kilograms right away. So it'd be 0.03 kilograms, okay? He lifts that 30-gram box from the floor and puts it over his head at 2.1 meters. So he lifts it 2.1 meters high. Okay, that's the distance. How much work did he do? Well, in this case, if you can think about it, right, if it's on the ground and then you lift it to a height of 2.1 meters, in order to lift that box up, the force you would have to use would be equal to the weight of the box. In order to lift something up, you'd have to push with at least the weight of the box. So the force of gravity on that box is the mass times, times 9.8. So 0.03 times 9.8 gives us 0.294 newtons, right? That's pulling down. So in order to lift it, we would have to push the lift force would have to be at least 0.294. So let's just assume it's 0.294. Then the work would be 0.294 times the displacement, which is 2.1. And we'd get work equal to 0.617 joules. Okay? So anytime you're lifting something, you can assume, unless they tell you differently, that the force used to lift it is going to be equal to the gravity or the weight of that box or that object. Okay? Now, if the force is at an angle, then we use cosine. So if the force is at an angle, then this equation becomes FD cosine theta. Okay? So not at an angle, it's just F times D. At an angle, it's force times displacement times cosine theta. Okay? The reason for that is, if you think about it, right? If we have a force pulling at an angle on this box, the displacement's in this direction, okay? The work that's done is in this direction also, to the right. So the part of this force that's pulling in that same direction, if this were theta, if this is F, this side over here is F cosine theta. This side here is F cosine theta. Okay, and we multiply that F cosine theta times the displacement. Okay. Another thing to make sure you note is that any force pushing perpendicular to an object's motion is doing zero work. So if I were to, let's say, here's a box sitting on the ground, and let's say I start pushing down on the box, but it doesn't actually move, right? Or it moves to the right or the left, then I am not doing any work, okay? And the reason for that is that if this is 90 degrees to the motion, so here's the motion this way, this theta is the angle between the force and the displacement. So if the displacement is to the right and the force is down, this angle is 90, cosine of 90 is 0. Okay, so this theta, I'm going to note that, theta is the angle between the force and the displacement. Okay, so and same thing here, right? If this is the displacement here, and it's there, that horizontal line, then theta is the angle between the force and the displacement. Okay. All right, let's go ahead and flip this here. All right, couple of new terms to define here. All right, so now we're going to move kind of into energy here. All right, so we have two types of energy. We have kinetic energy and potential energy. Okay, and we use Ke for kinetic, and we use Pe for potential. Pretty easy. Okay. The equation for kinetic energy is 1/2 mass times velocity squared. Okay. And kinetic energy is energy based on motion. Okay. Kinetic means motion, right? Kinesiology, kinesthetic learning, all those things have motion involved. So energy based on motion. So if you do not have any motion, or there's no velocity, you have no kinetic energy. And you can see that in the equation, because if velocity is 0, this whole thing is 0. Okay? Potential energy, the equation is mass times gravity times height. Okay? And this is harder, but basically this is energy that is stored. And in our case, this is gravitational potential energy. So it's energy that is stored based on an object's distance from the ground. Okay, so it's based on the height. So all objects have mass, right? There's going to be gravity on the Earth, right, or wherever we're talking about. And it's really the height that matters. So if an object has some height, then it has some potential energy. If it's on the ground, then this would be 0, and that would make the potential energy 0. Okay? The work kinetic energy theorem, I know this is a lot of information, but it's not going to be too crazy. Okay? Now, the work kinetic energy theorem states that the work is equal to the change in kinetic energy. That's what that triangle means, change in kinetic energy. Okay, this can be more easily written as work equals 1/2 final, so final kinetic energy squared, right? Final kinetic energy minus initial kinetic energy. Okay, so this is the more easily used equation. This says right here, this is the final kinetic energy minus the initial kinetic energy. So it's the change in kinetic energy is equal to the work. Okay, and we're going to go ahead and do an example on this using that theorem. Okay. All right, so example, a 75 kilogram bobsled, so mass is 75 kilograms, is pushed along a horizontal surface by 2 athletes. After the bobsled is pushed a distance of 4.5 meters, starting from rest. Its speed, so its final velocity, is 6 meters per second. Find the magnitude of the net force on the bobsled. Okay, now we're going to go ahead and use this. Okay, we can substitute the equation for work in there. So remember, work is equal to force times distance. So I'm going to write this as force times distance equals 1/2. So final kinetic energy minus initial kinetic energy. Okay, and then I'm just going to plug in what I know. The distance is 4.5. I'm looking for the force. Mass is 75. V final is 6. Don't forget to square it. Okay. And then I'm going to go ahead, because this VI is 0, I'm just going to write 0 for this whole thing, because 0 times anything is 0. Okay. So I'm going to solve this side first. So 1/2 times 75 times 36. So this is F times 4.5 equals 1350. What's happening there? Okay, divide by 4.5, and I get that the force is equal to 300 newtons. Okay, so that's how we do those work energy theorem problems. Okay, you will have some problems where you just use these equations. Oh, sorry. But these you just plug in, okay? So it shouldn't be too difficult. All right, power. We're getting to the end here. Power is how fast work is done, okay? So power, we use big P, okay? And power is how fast work is done. So it's the work divided by time, okay? Which the units would be, well, work is in joules, time is in seconds, okay? Which we can also, and now we more commonly use this unit that we call watts. Okay, and we do use big W. So I know that can get confusing, so we have big W as a variable and also as a unit, but it should be obvious when to use the two things. Okay, if it comes after a number, it's most likely watts, like as in the unit. Okay, if it says W equals something, that's the work. All right, let's go ahead and do an example here. So an electric motor lifts an elevator, so a distance of 9 meters in 15 seconds by exerting an upward force of 12,000 newtons. And we want to know the power. Okay, well, power is equal to work over time. We know work is equal to force times distance. Okay, so we can plug that in. And now we can just plug our numbers in. So power is equal to force, which is 12,000, times distance, which is 9, divided by time, which is 15. And we get power equals 7,200 watts. Okay. Make sure you're in seconds down here, okay, and that these are in meters and newtons. All right, you don't want to mix up the units, because those three units, meters, seconds, newtons, are all built into a watt. And so if you're using minutes, that's not going to be equal to a watt. Okay, let's do one more here. 13 kilograms, so there's the mass. Sorry, 1,300 kilogram. Electric car has a motor which exerts 1100 kilowatts of power. So 1100 kilowatts is equal, kilo is 1,000, so we're going to add 3 zeros onto that number to get into watts. Okay, 1100 kilowatts of power. How fast is the car going after 2 seconds if starting from rest? We want B final. Okay. So I think what we're going to have to do here is use the power to solve for the work, and then go ahead and use our work energy theorem. Okay. So remember that the work energy theorem says work equals 1/2 mv final squared minus 1/2 mv initial squared. So we can actually just sub that in for the work. So if power equals work over time, right? Sorry, 1 second. Yeah, so if power equals work over time, then we're going to go power, which is 11 with 5 zeros, equals this. We'll plug this in. Our mass is 1,300. V final is what we're looking for. Minus, starting from rest, so this is just going to be 0 over 2. Okay, so I'm going to multiply by 2. Okay, so I get 22 followed by 5 zeros equals 1/2 1,300 VF squared. Okay, so now I'm going to multiply by 2 again and divide by 1,300, and then I'm going to take the square root to solve for the VF. So VF is equal to 58.2 meters per second. Okay, and that's how we do that. All right. So that's the end of this this lecture notes. We will do a couple examples in class, maybe 1 or 2, and then you'll work on your worksheet. Okay. All right. See you guys in class.